Hey there everyone, we're some students from Derby Uni on the computer science course, and we're here to help explain the basics of sorting algorithms in a way that should make it easy for anyone to understand, even if they have no idea on how to use a computer. Throughout this video, we'll mostly be explaining the ideas around a deck of cards instead of a large dataset that could easily get pretty confusing. So let's say we begin with a completely random, unorganised pile of cards. How do we go about making sure it's all in order? Well, there's many different ways to go about doing this, but each one of those would be a different sorting algorithm. It's just a set of rules and processes we keep applying to the cards until they're all in order, and we do one last check to make sure it's sorted from lowest to highest. We're going to cover 5 of the most common, like the bubble sort and insertion sort, and then we'll compare how good they are against each other. But to do this, we'll first have to go over something called a time complexity. To make things easy for everyone to understand with the idea of time complexities, we're going to have to simplify it a bit and use the example of food and cooking a meal for n number of guests. Because even as computing students, it was pretty confusing for us to understand this idea. So, all of these aren't necessarily as time as in seconds, but in something called big O. It means it's easier to compare each algorithm, but it can get tricky knowing what they mean. So let's start with the simplest, O1, the constant time. For our food example, this would be like having the same meal cooked at the same speed no matter how many guests you may need to cook for. It always takes the same amount of time. Next up is ON. This is like grilling steaks for each guest. The time it takes to prepare the meal is based on the number of guests. Simply, if you double the number of guests, the preparation time will double. Then we have ON squared, where you need to prepare a custom dish for each pair of guests. Maybe you're making special combinations of food for each possible pair of people. But if you add more guests, the preparation time it takes increases by 4 times as many. Then come the logarithm times, starting with O log n. This is like dividing your guests into smaller groups and cooking a large dish for each group. As the number of guests increases, the number of dishes you need to cook grows logarithmically. And finally, we have ON log n. This is like deciding to cook a different dish for each guest. But thankfully, you've got some help this time around, because it's like using a recipe book that's sorted by the type of food. Then finally, there's the space complexity. This, in our food example, is like what we need to store to make all our meals. So maybe it's a recipe book, or it's some trays to store each meal. It's just something that we have to deal with that changes from algorithm to algorithm.
Those basics out of the way, let's work on our first sorting method, the insertion sort. This works by going over the dataset and comparing the current item we picked to what came before it. If our current item is smaller, then we check the next item before, and so on until we find one where our current item is bigger. So to make space for it to be sorted, we move all the bigger items up one space and slot in our current item. The best real-world way you could use this is by organising tasks on how important they are, like how I plan to make this video. For the time complexity, the best outcome is just ON. You have to go through all the items in the list, so it depends on how big the list is, but they could already be sorted, so you only have to check them all once. The most common outcome is you may need to go through the list a couple of times, and that's how you get ON squared. You'd need to go through the list of n times to pick our current item, and then you need to check it against all other items n times. This also happens to be the worst possible outcome for the list when it is completely unsorted. For the space complexity, well, that would stay the same no matter how long the list is, with us only needing to keep track of our current item, so for that we get O1. Insertion sort is really easy to implement and explain. It took me less than 100 words to talk about the basic idea of it. With the longest time it could take being ON squared, it works great on small data sets, but if we had to use with 100,000 cards, that would take a long time. There's only needing to keep track of what our current item is and our current space complexity of O1. It's an in-place sort, which can be handy for not using too much of your computer's memory. And with how the algorithm checks, if it comes across 2 of the same item, it won't change the order of them, which is really useful in some cases. We'll call that a stable sorting algorithm. Next up is the bubble sort, where each item is picked and compared against the item next to it. Then the higher value item of the 2 is placed on the right, and then we do the same thing with the next item. After the first pass, the largest item should then be on the right. This can be called bubbling up, as even if the largest item is on the left, we'll still swap it all the way up as we check it against the following items. We repeat this process until no items are swapped, meaning our list must be sorted from lowest to highest. The best case for this kind of sort is ON, simply because we need to check through the whole length of the list, and if we do no swaps, then it's sorted already. Most likely though, we will need to make ON over 2 passes, but ON comparisons, so we simplify this to ON squared. And then the worst case is where we need to make ON passes and ON comparisons, that's also ON squared. Like selection sort, because we have no extra variables to keep track of, we have a space complexity of O1. With how we sort the list and just making comparisons, we don't need any memory outside just storing the list, and with how efficient it is with the best case of ON for a sorted list, we can use this instead of the selection sort. It still falters like the previous ones when it comes to large datasets though, with the worst case of ON squared being a common problem that our next algorithm should fix.
The merge sort divides up the data to effectively sort it, meaning we finally have an algorithm for the larger sets of data. The list is constantly divided in half until we have separated all the items individually. Then we build it back up by comparing pairs and putting them in order until the full list is reassembled. Because of how we're sorting the list every time, the merge sort only has a single time complexity of O n log n. So no matter the state of the list, we're still performing the data operations to it. The space complexity changes here unlike our previous algorithms to ON, as we're having to create space for each individual item to be stored before we build the list back up. Because we perform the same operations no matter the size or state of the data, we have a guaranteed time complexity, but it's better suited for larger datasets where an algorithm with ON or ON squared may fall short. This does mean though that using it against a smaller dataset may take longer than those types of sorts, so the merge sort has its purpose when you know where to use it best. The merge sort is another stable sort. The specific order of equal items stays the same, but it isn't an in-place sort due to it needing to create a separate space for each individual item as shown with its ON space complexity. Our final sort we're covering today is the quick sort. To do this type, we need to first pick a pivot point in the list and set some pointers. A left pointer for the first item in the list and a right pointer for the last item. If the item at the left pointer is less than our pivot, we move that pointer to the right until our pointer is greater or equal to the pivot. Then we do the same with the right, moving it left until the pointer is less than or equal to the pivot. If the left pointer is less than or equal to the right pointer, we just need to swap their values and move the left pointer to the right and the right pointer to the left. To know our sorting algorithm is done, the left and right pointers should meet. Our target complexities are ON log n for the best, and this happens when we pick a good pivot point, usually the mean of the data. The average time it will take is ON log n, where the list is split into two, with one being k items long and the other being n minus k long. The worst case occurs when the list is split into two equal parts, and this will take a time of ON squared. Thankfully, our space complexity is simple with O1 with two consistent pointers. With our divide and conquer strategy, it makes quick work of large datasets, but it is not effective against smaller datasets. With our divide and conquer strategy, it makes quick work of large datasets, but it is not effective against smaller datasets. And with only needing two pointers to function, it needs a small amount of memory to function. Due to how we're swapping our items, it means this is not a stable sort, so any equal items may have their positions swapped. And that's all our algorithms explained. They all have their own specific use cases, so if you have to pick a best, it's for whatever case you need to use it for. You wouldn't use an insertion sort for a 100,000 item long list, but you could use a merge or quick sort, so be smart and make sure you use the right algorithm for the right task. That's it from us. We've been some second year computer science students explaining sorting algorithms after working on this video for 4 weeks. But a word of advice before we go: never use bubble sort, just don't. See ya!